Okay, so now in this video, today I just want to discuss drawing free body diagrams. Okay, so free body diagrams. I don't know why I put it down like that, but here's what it is. So free body diagrams. So we've understood forces to some extent. We understand how forces work, right? If I say that there's a force of 10 newtons acting on this ball, that means I'm saying that this ball's momentum is increasing by 10 Newton meters per second in the positive x direction. Okay, so that means that this ball's momentum is increasing by 10 Newton meters per second in the positive x direction, right? That's what this diagram here means. Okay, now free body diagrams is to draw diagrams on it's to draw diagrams to explain what forces are acting on an object. So for example, let's say I had a mug, right? Let's say I had a mug on a table like this. I have a mug on a table like this. I don't know why I'm using a mug. Might as well just use a board, mate. Just easier to draw. So let's say I have a ball which weighs 5 kg on a table like this, and the table is on the earth, okay? And I say draw the free body diagram of the ball. Draw the free body diagram of the ball. Now, what does this mean? I'm asking you to essentially label all the forces that are acting on this ball. Okay? So I want you to label all the forces that are acting on that one ball. How do you do it? And free body diagrams, you draw them for one object at a time. So remember this, that free body diagrams are drawn for one object at a time. So this is what I'm essentially saying here is you can draw a free body diagram for the ball, right? Free body diagram for the table. You can draw a free body diagram for the floor. Okay, you can draw a free body diagram for all three of these. But when you draw the free body diagram, you put down all the forces that are acting on the ball. Okay, so one force that we know is acting on the ball is the force. Now I'm going to draw the free body diagram. Okay, so 5 kg here. I'm going to draw the free body diagram. So one force that I know which is certainly acting on it is gravity. Okay, done. So gravity is acting on the ball. However, this ball is not falling down. It's not moving up, nor is it moving down. It's got zero motion, which means right now it's got zero momentum. The force of gravity is increasing the ball's momentum in the negative y direction. Okay, so one more time, the the gravity force which is acting on the ball is increasing the ball's momentum in the negative y direction. So the ball's momentum is going uh, up, is essentially increasing, and the ball wants to start moving downwards, but it is not moving downwards. This means that there must be another force on the ball, right? So there must be another force on the ball equal to G but opposite. If there's a force like this, okay, now this G and this G are different. This is not Newton's third law. There's two forces acting on it, yes, but this G is the gravitational force And the reason that there's another G going upwards is because there must be a force that is balancing the G force so that the ball does not move downwards into the table and breaks the table. Okay, so let me just draw that on this diagram here. So we got 5 kg here. Sorry, 5. Why am I even putting 5? So we've got G here, the force of gravity acting downwards. Then we must have something to balance it, which is up here, which is G. Now, where is this force coming from? Right? So the question is, where is this force G coming from? This G, this upward force G, must be being put into the ball from somewhere, right? This upward force G is actually coming from the table. So the table is experiencing a force down here. Okay, this G is not due to gravity, rather it is due to the ball. So this here, Newton's third law. Okay, equal and opposite forces. Right? Now, is this balanced? Yes. There's no forces and no forces. It's not moving. There's no forces. Does this seem correct? Yeah, this seems correct. This is correct. So this is all the forces acting on the ball. This is the free body diagram of the ball. This is the free body diagram of the ball. Now I'm going to draw the free body diagram of the table. Now the table looks like this. Here we have the table, right? This is the table. So what forces are acting on the table? From this blue arrow, we already know that there's a downwards force on it, on the table, which is equal to G here. This is due to the ball. This is Newton's third law in action. This force and this force on the ball are connected, okay? As the table loses momentum per second, that momentum per second that it loses is being transferred into the ball. Or actually, as the table gains momentum per second, as the table experiences the force is being transferred from the ball. So the ball is losing momentum, right? If going downwards is gaining momentum, then going upwards is losing momentum. So this force is saying, the blue force on the ball is saying that the ball is losing momentum per second, and the blue force on the table is saying is that the table is gaining momentum per second. What's happening is that the momentum from the ball is being transferred into the table. Newton's third law. Okay, so that's what's happening. That's why these two blue forces are connected. Next, we know that the table's got its own mass, so it must be experiencing a force G due to gravity. However, sorry, I just need to check if I'm still recording. Yeah, okay, I'm still recording. So now you see that if there's two forces of gravity acting on the table should be moving downwards, but it is not moving downwards. Okay, the table is still. That must mean that there's another force on the table that is pushing the table upwards so that it does not go through the floor. So this force must be coming from the ground. Okay, and where is the table in contact with the ground? The table is in contact with the ground right here and right here. Okay, so And these two forces should be equal to G, so that the two G's cancel out these two G's, and essentially the resultant force is equal to 0. Okay, so that G, G plus G is equal to 2G. Okay, I hope this makes sense over here. Essentially what I've done is I put down these forces, right? And now when you see it like this, all the forces are now balanced. There's not an increase in momentum or a decrease in momentum per second of the table. The table stays still, and this is now correct. Okay, now let me scroll down. Let's do the force. Let's do the force diagram on the floor now, right? So here we have the floor. Let's do the force diagram on the floor now. So on the floor, we've got these two G's. But where did they come from? They can't just have appeared from somewhere. Something must be, Newton's third law must apply here as well. So what we have here is that it's coming from the ground. The ground is experiencing a force downwards in these two locations like this. Okay? Connected. These two and these two are connected. Newton's third law, which is that an action has an equal and opposite reaction. Notice that Newton's third law does not act on the same object. In terms of this, we've got a force acting on the table, and the other equal and opposite force is acting on the floor. Similarly, if I go back up to the ball example, we've got a force G acting upwards on the ball, right? The red G is the gravity, and then we've got this blue G acting upwards on the ball, and this blue G acting downwards on the table. The blue G acting upwards on the ball is equal and opposite to the blue G acting on the table. Sorry, I speak a little mixed up sometimes, but essentially, I hope you understand what I'm saying. I hope you get my point, right? So that's what Newton's third law is. Also, okay, let's continue practicing. I'm going to make another force diagram, right? Okay, so let's say I have a sloped surface like this, and I have a box on the sloped surface, and sorry, and I say box. Let's draw the free body diagram on this. Let's draw the free body diagram on this. So we got this, okay? On the box alone, let's separate the box and the floor first, right? So the box is like this. Let's just draw the free body diagram on the box first. Box. So firstly, we have gravity acting on the box like this. See? So we got G, right? Next, okay, so we've got G here, right? Now the next thing I want to do is I want to split this force into its horizontal and vertical components. This angle here will be theta, okay, which is the same as this. But if I split it into its horizontal and vertical components, And by horizontal and vertical components, because I haven't taught it yet, what I mean is, for example, let's say you have a grid, right? Like this. You got X, you got Y, and let me just draw a force on here, like this, right? F. This F force, I can split it into its vertical and horizontal components. Okay? So I have it like this, and I have an angle. Its horizontal component, this vector's horizontal component, will be F cos theta, and then this component here will be F sine theta. Okay? So that if I do F cos, so that if I do F cos theta plus F sine theta, I get F, right? So what does this mean? So F will have coordinates something like, so this is 0 obviously. So F will have coordinates something like 3, and then this could be like 5. Okay? So it'll be 3 on the X, 5 on the Y, right? So F cos theta, this arrow here, will just have coordinates 3 and 0y, plus, and F sine theta will have coordinates 5, will have coordinates uh, 5, 0, because it's not bending into any of the x direction. It's just straight up. So it'll just be 5 and 0. No, not 5 and 0, it'll be 0, 5, because it's not moving. If this arrow here essentially was something like this, right? We could say this arrow is moving 2 to the left, and then 5 up. If this arrow is straight up, that means this arrow is not moving anywhere to the left or right, and it's just 0, 5. Okay, like that. Okay, so I have 0, 5. When I add this up, you just add the top and bottoms together, and you get 3, 5. And this is essentially the exact same as this, alright? If you don't understand F cos theta and F sin theta, don't worry about it too much. Essentially what I'm doing is just splitting it into its horizontal component and the vertical component. So rather than having it the graph exactly like this, I can have the graph in this shape, right? I can have the graph in this shape and draw a line like this and say what's the coordinate here and what's the coordinate here, and I'm essentially splitting it into its horizontal and vertical components in this way. Essentially, I'm changing the reference frame, kind of. Well, not kind of. I am changing the reference frame. Don't even worry about what I said, because some words I say even I don't know the meaning of. Regardless, I'll split this into its horizontal and vertical components. This here. So now when I've split it into its horizontal and vertical components, it's going to look like this, right? So now I'm going to draw the box again, but I'm going to exclude this force and use the horizontal and vertical components of this force. So this will be G horizontal, G vertical, right? So G horizontal plus G vertical equals G essentially, right? So that's what I'm putting down. And these are all vectors. All vectors, just put like a hat above them, right? All vectors need like a hat or like a line above them or something like that. Now the next part of all of this is the following. So you've got the box like this, okay? the gravity force, rather than putting the gravity force, I put its vertical and horizontal components like this. So I put GH and then GV. So we've got these two forces acting on the board, but I said that the box is in equilibrium, which means it is not moving. The box is not moving. So there must be two other forces that act on the box. There must be two other forces that act on the box such that the box does not. Okay, so for example, we've got the GV and the TH, but one force that you're missing is the force of friction, in the sense that if the box is trying to move in this direction, friction will always oppose it. So we can say that friction is acting on the box like this, Fr for friction. And then to oppose this G horizontal force, you've got the normal force. Okay, normal force. Now Fr equals GV. And then GH, G horizontal, is equal to the normal force. This puts the box in equilibrium. I hope that made sense to you, because if only this force existed on the box, then the box would go through the slope. However, it's not going through the slope, which means there must be another force that's acting on it, which is the normal force. Also, if only this force was acting on the box, then the box would begin to move downwards, okay? Like this. The box would begin moving downwards. But it's not moving downwards because there's a friction force acting on the box, which is stopping the box from moving downwards. I hope that made sense. I think that should be enough for this video. I really hope you understood all of that. Um, in the next video, we'll probably study gravity or something like that, right? Thank you.